Hi guys, this is a calc video, 6-6 for Friday, February 10th. The homework associated with it is these two problems on page 11. So let me just summarize real quick this unit. We have, so you're finding area and volume. So we found the area between two curves. Then we found the volume of solids with known cross sections. Okay, that's like if you know you've got a certain solid, but then each cross section perpendicular to either axis would be like a different type of geometric plane, like a flat surface, I mean by plane. And now we're going to have volumes of solids of revolution, okay? So I'll show you what that is. So let R be the region bounded by this graph, that graph, and the x-axis. Find the volume of the solid generated by revolving the region R around the x-axis. Okay, so first we want to draw the region. Okay, so I'm doing an xy axis. And, okay, y equals radical x. Okay, that looks like this. Okay, that's that. X equals 25. That's the vertical line that goes through 25. The x coordinate 25. Okay, so this is x equals 25. This is y equals radical x. And the x-axis, this is the x-axis, and that's y equals 0. Okay, so the region is bounded by these curves. So I find the intersection points of those curves. So that's these. Think of these as the vertices of your region. So your region is this right there. Okay, so that's our region. And what we're asked to, or let me find these intersection points first. Okay, so this one is 25, 0. This one is 0, 0. This one, the x coordinate's 25. And then for the y coordinate, I would just plug it into that function right there, so I'd get 5 for the output. Alrighty, so find the volume of the solid generated by revolving this around the x-axis. So let me show you a little bit like what that would look like. So I did this in class, so I cut out this. Okay, so this is supposed to be the graph of that. And the blue stick is the x-axis. Okay, and then what I would like to do here real quick, so we're revolving around this, so go like this with me, guys. Okay, anytime you're doing a solid of revolution thing, I would do a little circle and show like what you're revolving around. So what I mean by doing this is that the stick is going to be turning, okay? The stick is going to be turning, and as it does, the region turns with it. So all right, I'm going to show you what that would look like. So I'm going to move this a little bit. Okay, so can you see that? Yeah. All right, so here's the region right now. The x-axis is this blue stick that I have it attached to, and it's rotating. So the x-axis is turning and the region goes with it. And guys, as you do this, I'm glad I'm doing, this looks much better on camera than it does in real life because there's a little bit of a delay. So, and for that reason, I don't know, it is looking more like a solid. So as I rotate it like this, we get like a solid shape. Okay, so you can kind of imagine that. We get a solid shape. And the cross sections of each, if you sliced into this solid shape, each cross section would be a disc. Okay, so back to the paper. Alrighty, so it's gonna be very much, I'm gonna use a chart very much like I did the solids of known cross sections, except instead of perpendicular to, we're gonna say revolves around. Okay, so revolves around. Okay, and then we're going to draw a cross section. And then we're going to find its area. And then to find volume, you add up an infinite number of areas. So if we want to add up an infinite number of these areas, we'll put it inside of an integral, a definite integral. We're revolving around the x-axis. Okay, so that means that we want everything in terms of x. The cross section is going to be a disk. And so what I'd like you to do is this, guys, and please do this in the same order that I do. So since we're revolving around the x-axis, so I'm going to take one cross section, and I'm first going to put a dot on what I'm revolving around, and I'm going to put a C on that dot because that's going to be the center of my cross section. Then I'm going to draw a line from the center of my cross section all the way till I hit the end of the region. Okay. So that, and then I'm going to put a little R on that because that's going to be the radius of my cross section. And now this is the part where it's hard for me to draw this. I can never make this look good. But so if we cut through the shape here, the cross section would be like, oh, let's see, I can't do this. All right, so this would be the cross section right there. Okay, so the cross section, all right, so this pink line is the same as this pink line that I'm drawing. So right there, okay, so there's the center. Okay, there's the radius right there. Okay, so this is that. And then I'm gonna draw, I don't know if that helped or not. Okay, so then I draw the rest of the disc and I fill this whole thing in. And then down below I'll say what R is. Okay, so to find this radius, you ask yourself, to find a vertical length, you do top minus bottom. If I wanted to find a horizontal length, I'd go right minus left. But vertical length, so top minus bottom. So top minus bottom, this is radical x minus 0. Okay, so the radius is radical x minus 0. Okay, so the area of this, and you could just say radical x. So the area of this is a circle, so it's going to be pi r squared. And what is the radius? It's this right there. So pi radical x. So this is pi x is the area. Now, to get the volume, we have to do an integral. So I'm going to do the integral from x equals, everything is in terms of x. So for the region that I'm working with, the lowest x value is 0. So from x equals 0, the highest x value is 25. And then what goes inside of the integral is the area. So pi x. All right. This is really easy to do the fundamental theorem with, so I'll just do the fundamental theorem. So I'm going to do brackets, 25, 0. What goes inside of the bracket when you're doing the fundamental theorem? That means finding the integral without a calculator. The antiderivative of that, so it's going to be pi over 2 x squared. This is equal to, you plug in 25 and then you subtract what you get when you plug in 0, and we're going to get 625 over 2 pi. Or I can say 625 pi over 2. Okay, so there's that. Now another one, let R be the region bounded by this parabola, the x-axis, and the y-axis. Find the volume of the solid generated by revolving R around the y-axis. So that's how this will be different, revolving around the y-axis. And this is the only other example for today. So I'm going to draw a xy axis. Okay, that's pretty slanted. And then this is an upside down parabola. The x-axis is right here, so that's the graph of y equals 0. And then the y-axis is here. That's the graph of x equals 0. So I'm intersecting, the x-axis intersects the parabola here and here. The x and y-axis intersect each other there. See, I have to put dots where all three of these intersect. And then the parabola is intersecting the y-axis there. And now this is kind of confusing because either, oh, let me see. Huh, okay. There's actually two ways that you can do this. Revolving around the y-axis. See, this confuses me. It's going to come out the same way, but either these three are the vertices, or these three are the vertices, or these four are the vertices. I don't know. It's not actually going to matter in the end. All right, and I'll show you why. I'm going to do, crap, I'll do these three as the vertices. Okay, so I'm kind of like leaving this one out, but it actually doesn't matter, guys, and this is why. Okay, so now here's the y, the blue stick is the y-axis, all right, and then I'm just taking like 1/2 there. It doesn't matter if I had, I don't know, even if I used this side instead, or if I used both sides at once, when you revolve this, can you see that? All right, when you revolve this around the y-axis, you are just getting this solid shape, very much like the top shape that we had, but just vertical, you know, standing up a different way. And whether I used either side or both sides, because it's symmetric over the y-axis, we're still going to just get the same, when this region sweeps through the air, we get the same solid shape. Okay, so it actually wouldn't really matter. Okay, so, alrighty, so this is, let me find these intersection points. All right, so this is 0, 0. This one here is 4, 0, and this one here is 0, 16. Okay, and then I'm going to say revolves around cross section area. So we're revolving around the y-axis, which means everything will be in terms of y. And so right away, guys, I know I need everything in terms of y, which means I have to solve for x. All right, so right up here, I want to solve for x here. So I would subtract 16 from both sides. I would divide both sides by -1, and then I would take the square root. So we get that y is equal to plus or minus radical 16 minus y. All right, so y equals the positive, no, x, my bad. X equals the positive one would be this right side. X equals the negative one would be that left side. So the positive, so this over here, x equals radical 16 minus y. Yes. Okay, because I needed everything in terms of y, so I solved for x. Okay, now, just like I did before, this is, okay, so I'm rotating around the y-axis. All right, so I go along the axis I'm rotating along, I find a point. Okay, this is going to be the center of my cross section. That will be the radius. And then, I guess I'll use blue. All right, and then I just imagine when I'm rotating this, I get that cross section there. Okay, so that disc right there, that's going to be our cross section. And then I go over to this cross section space. So here's the center, there's the radius. Okay, so center, radius. We get a disc when we revolve everything. And then I just have to figure out what the radius is. So this pink radius is the So that's the radius I want. So I have to do right minus left because it's a horizontal length. So right minus left, right minus left. So right would be radical 16 minus y, and left would be 0. So right minus left, radical 16 minus y minus 0. So the radius is radical 16 minus y. Okay, and then for the area, it's pi r squared. So it's pi radical 16 minus y squared. So this is pi times 16 minus y. And then to get the volume, you put the area inside of an integral. So you go the integral from y equals, the lowest y is 0, the highest y is 16. All right, and then what goes inside here is the area. So pi 16 minus y. And I'll just tell you what it is, okay, to save time. So let's suppose I use my calculator. Actually, darn it. What time is it? Okay, guys. All right, I'm going to do this without a calculator. All right, so I'm going to pull out the pi because I just think it'd be easier that way to not have to deal with the pi inside. Okay, so I pull out the pi there. And then, okay, so I'm moving over here. So I'm going to have pi, and now I'm going to take the antiderivative. Okay, antiderivative of this is 16y minus 1/2 y squared. All right, so this is equal to 128 pi actually. 128 pi. Alrighty, and if you used your calculator, you would get an irrational number, which would be equal to that. Or a decimal, which would be equal to an approximation of that. Okay, guys, so there is that, and I will see you soon. Bye.